Well, thanks for joining me, everyone. Like the good intro, we're going to be today talking about scriptable render pipelines and why they're so interesting for mobile game developers. I'm Yilmaz Kiymaz. I'm from InnoGames in Hamburg, Germany. You might know some of our titles. Let me actually switch over to the presentation here. Okay. You might know some of our titles, such as Forge of Empires, Elvenar, Warlords of Eternum, which was recently launched, Tribal Wars, Greplis, Tribal Wars 1 and 2, of course, and the West. So let's first get a round of hands in the room. How many of you have looked into scriptable render pipelines already? A few hands go up. How many of you have upgraded one or more of your projects to use either the lightweight rendering pipeline or the HD rendering pipeline? Okay, a couple more hands. It's good. So most of you probably already know that the built-in render pipeline in Unity is kind of a black box and has been for many years. It has always been difficult to extend and make little tweaks here and there. We had to resort to many different workarounds that weren't very maintainable over the years to be able to do something different with the render pipeline. So as a solution to this, Unity has come out with scriptable render pipelines. And you probably already know that there are two scriptable render pipelines that Unity is making available via the package manager already. The high definition render pipeline, which is targeted towards PC and console for games with high graphics requirements, and the lightweight rendering pipeline, which is targeted for games with low graphics requirements and also for mobile games. There have already been some good Unite talks on these topics, such as the Unite Berlin 2018 and Unite LA 2018, both from Unity themselves, that do a great job at introducing people to these different pipelines and what scriptable render pipelines mean in general. So I won't go too much into what these are. I will rather specifically focus on the lightweight render pipeline and why it makes sense to upgrade to it if you're making mobile games. So why should we optimize our mobile games by upgrading to the lightweight render pipeline? You might be saying, well, I'm already hitting 30 FPS or 60 FPS on the devices that I support. What sense does it make for me to further optimize? Well, the thing is, unlike on desktop or console, where hitting the target FPS is enough, on mobile, we actually have to worry about not draining the battery of the user too fast or letting the devices get too hot, because people do complain about that. It reflects on your reviews, etc. So it's always worth it to optimize further to improve your battery usage. Some of you might be familiar with this view on Xcode that shows how much of an energy impact your app is having on the device at the moment. So Unity, unfortunately, even when you run an empty project, an empty build on a device, it already has kind of a high battery usage. So you always have to make sure that your code and your graphics aren't pushing the device too hard. So what we're going to look at is how we can convert a shader that was written for the built-in rendering pipeline into one that is compatible with the lightweight rendering pipeline. Because the talks that I mentioned talk about how you can upgrade your project if you're using the standard shaders that come with Unity, but they don't talk about how you might upgrade your custom shader that you've written for your mobile game, which we have to do most of the time to get the performance we need. So we're going to switch over to the other scene that you saw in the beginning. Here's a little scene, ground plane and 5 farm animals that I grabbed from the asset store for free. And the interesting thing about these is they all share the same material, and the material is named Vertex color, which should give away the fact that these models, what's special about them is that they're using Vertex colors for the kind of texture you see on them. There is no actual 2D texture that's being used to paint them. And I have a shader here that is compatible with the built-in render pipeline, what's been there for most of the time, and I have some properties here to show you what features this shader has. So this shader can be affected by the ambient lighting in the scene. If I drag the slider, you can see the result, that the ambient lighting goes away. It can be affected by diffuse lights. Hang on. So if I turn it all the way down, you can see all the diffuse light, all the light from the directional light has gone away, and the shadows have gone away. And then there's the vertex colors. So if I turn that off, you can see there are no vertex colors on the meshes anymore. So this is a very simple shader, and I chose this shader because first, it's a very reasonable approach to how you might want to style your game and how you might want to create art assets for a mobile game, because Verity doesn't have high performance requirements. And also it makes it the shader simple, and to show that how to upgrade to the lightweight rendering pipeline, it makes that simple as well. So if we were to switch over to the lightweight rendering pipeline, which you do by going to I actually have it right here. I don't. Project settings, and then graphics, and then dropping in a lightweight render pipeline asset right here. That's how you switch your project to use lightweight render pipeline. I have a small shortcut here that I did for this presentation where I switch over to it. You can see in the bottom left corner, it says lightweight render pipeline. If I switch back, if I can, it's a built-in render pipeline, lightweight render pipeline. Everything's pink. So this is usually what you see when you first put your lightweight render pipeline asset in there. None of your shaders are compatible, so everything is pink, which is the hidden internal error shader that Unity is using to show you that something's wrong. So what can we do to actually make our nice vertex colored models appear with the lightweight render pipeline? The first easiest thing might be to use a new shader graph. And it's relatively easy. We're just going to go ahead and do it right now. I'll just go to my shaders folder, create a new shader with a PBR graph. PBR stands for physically based rendering. We don't actually need physically based rendering in our game, but with the new lightweight render pipeline and the shader libraries, they actually did put a lot of defines in place to strip out a lot of calculations if you're not using it. So in theory, you shouldn't be paying for things that you're not using, but we'll come to that a bit later. So I create a new one. I want to give this specific name so I can switch over to it. And then, oh, wrong name. Hang on. Okay. Empty shader graph shader has a PBR master node. What we want to do is just feed in the vertex color of the mesh into the albedo channel. So we create a new node, search for vertex color, and then feed it into the albedo. And for it to produce pretty much the same result as our previous legacy shader, we just need to set the smoothness to 0, save it, and then we go back and change our material, the one material that every mesh in the scene is using, to use this new shader graph shader, which is right here. And just like that, our project is now using lightweight render pipeline and is actually rendering the scene correctly. And if we kind of switch back and forth, you can see at the bottom left, I'm switching between built-in and lightweight render pipeline, and you can barely notice any changes, I hope. Let's make sure in the scene view, let's get it up and close a little bit. So what you can see, some differences is the shadows appear a little bit different, and that's just because of the way they're handled, the shadow bias parameters that determine at which point they stop intersecting with the geometry. That's a little bit different, but besides that, the mesh themselves actually look the same. The lighting looks the same besides the shadows. So okay, this is nice and well. We have our scene working with the lightweight render pipeline with this graph. But when you're making mobile games, you always want to write your custom shaders to achieve the best performance, right? Especially if you're making a game that has high graphics requirements. So it's always good to know how to write shaders by hand, and we're actually going to take a look at that now, what it would look like to make a shader that's compatible with the lightweight render pipeline. Luckily, I have one pre-made here. I just want to double check that I'm switching to the correct one. Yes. So we first look at the legacy one, and then we look at the new one and see what it takes to convert a shader to be lightweight render pipeline compatible. So here's our legacy vertex color shader. How many people here are familiar with writing shaders in Unity like this? Okay, good number of hands go up. If you're not too familiar, don't be too scared. It's just 100 lines of shader code, and it's really not that different from writing regular C# code. You should be able to follow along. And if you don't, ask questions at the end, no problem. So here I just declare the properties at the top that I showed you in the beginning to be able to turn on and off the ambient lighting, diffuse lighting, and the vertex color. That's that. We have one sub-shader with 2 passes. This is the forward base pass, and at the bottom we have a shadow caster pass so the meshes can cast shadows into the scene. This pass takes care of receiving the shadows. So here we don't have many options specified in the pass, such as Z-write and color mask and this and that. We just immediately get into the CG program. We say our vertex shader is named vert, as you can see here. Our fragment shader is named frag, which is down here. Multi-compile forward base enables the shadow casting abilities, shadow receiving abilities. And then what I try to do with these shaders and the one that I'm going to show next is I try to minimize the number of include files I use, so everything that is done in the shaders is as obvious as possible right here instead of using magic methods from Unity. There are a few here and there. So include the Unity CG.cg include file, which is like the base include file, and then the auto light, which has a couple of nice helper methods for lighting. And then we redeclare the properties that we declared up top, which is necessary for the CG code to work. This is for the main light color. And we have two structs. One is for attributes, which is what Unity provides us in the Vertex shader to work with, and the varying structs, which is what we calculate in the Vertex shader and gets sent over to the Fragment shader. So the Vertex shader is pretty standard. We calculate the clip space position of the vertex from the object space position that we're given, just a built-in Unity method that does that. We calculate the world space normal from the object space normal, again, built-in Unity method. We directly pass over the vertex color from the input that we get out to the output, and it will automatically get interpolated by the GPU. Here's a macro, again, from Unity that transfers the shadow coordinates. And Vertex SH, spherical harmonics, is for being able to evaluate the ambient lighting. So again, built-in method, shade SH9, where you just pass in the world space normal, and then you get your ambient lighting. So all of these are fed into the output structure, and then we just return it in the Vertex shader. Then we come to the Fragment shader. At this point, the GPU has done the job of interpolating this data for us per fragment. In the Fragment shader, we normalize the input that we got, because when normals are being interpolated, they can get unnormalized, which means their length is no longer 1. So when you renormalize it, you get nicer and more correct lighting. So we do that, and then we calculate something called n.l, which means if there's a light in my scene and it's hitting my mesh at a specific angle, the specific pixel that I'm trying to calculate, what is the angle there to the light, which affects how bright that pixel will be. So that calculation is done here. Then we multiply the color of the light with this factor, with the shadow factor, and this diffuse contribution I just added there to be able to turn it on and off. And then we add the ambient light to the directional light, and finally we get the vertex color. Normally we could just use input.color directly, but here, because of this slider I added, I'm just interpolating between the actual vertex color and just white, which is 1, 1, 1. And in the end, we multiply the diffuse color with the vertex color, and we return that. I won't go into the shadow caster pass because it's very standard. You can just copy it out of an existing Unity shader like this. So this is what the shader looks like. The interesting part is just like 40, 50 lines. What does it take to make this lightweight rendering pipeline compatible to convert it over? So let's open that one. Looks pretty much the same. I mean, if I switch back and forth, you can see it's more or less the same. The first difference we see is that the CG program line has changed for HLSL program. They're kind of just like different flavors of each other, so there isn't that much difference. So instead of starting with a CG program and ending with an NCG, we now start with an HLSL program and end with end HLSL. Not that much different. Again, we have a couple of pragma statements. These are kind of specific to the lightweight render pipeline, and I just basically copy them over from an existing lightweight render pipeline shader. Here we specify our vertex and fragment shaders. And again, we have an include file. And what's interesting with this string is that the lightweight render pipeline comes in as a package, right? So it's not something directly in your assets folder. It's here in packages. So how do you then reference some file that's in a package? And this is how you can do it. Nope. Just type packages and then the whole path down to the, in this case, the lighting library. And then what you have to do with the Scriptable Render Pipeline shaders, if you want them to batch properly, is you need to use these C buffers, which stands for constant buffers. And what the Scriptable Render Pipelines can do with their new experimental batching is that they can put all of these into a linear array and render multiple meshes in the same path. So with the previous built-in renderer, you could only batch together meshes that would use the same material with the same properties, more or less. With the new Scriptable Render Pipeline and the batching that they have, it's possible to batch together many meshes that share the same shader, the shader variant specifically. So you can batch together many more meshes than before, and we will actually be able to see it in a little bit. So just like before, so instead of just putting them like this, we have to wrap it with a C buffer start and end, no problem. The attributes and the varying structs are pretty much the same, actually almost exactly the same except for the names of the variables. And then we have the vertex and fragment shaders here that do very much the same thing. So the name of the methods, the internal Unity methods, have changed a little bit, which you can find out in the shader libraries of the lightweight render pipeline, but besides that, it does exactly the same thing. So you don't really need to change much. One thing that threw me off when I was converting my shader is in the built-in render pipeline when using CG, you could use a fixed, what's the word? Precision specifier, which is valid. But in the new Scriptable Render pipelines, there is no fixed in HLSL. So there's half and float, and I think another one. But I just converted all my fixed precision modifiers to half, and that's it. And basically, that's it. There isn't much else to it. What I would like to show you is what the package looks like. So here's the Lightweight Render Pipeline package. And here it has the shaders. There's a lit shader, which is a PBR shader, and then there's a simple lit shader. So basically what I did to be able to create this lightweight render pipeline compatible version of my shader is I opened the simple lit shader and copied stuff in from here. But the thing is, if you look, there's a ton of stuff in here. There's all these PBR-related stuff like shininess and gloss map and specular map, which I'm not using in my mobile game, right? So I had to cut all that out. And the other thing is all the different passes, they don't have the vertex and fragment shaders in here. They get included from another file, simple lit forward pass. So if we open that over here, you can actually see the structs and the vertex and fragment shaders here. But basically then these guys include some other include files such as here, and then you have to go in there and copy some stuff over. So what I'm still trying to find out is there a way to extend built-in shaders without having to copy everything over and then just modify it a little bit, and then you forget what you modified and have to include comments everywhere. I asked these questions to the Unity graphics team, but haven't got an answer yet. But hopefully it will improve. Yeah. So I want to demonstrate to you what the new batching, how much of a difference it makes. So switching back to the, if I can, built-in render pipeline. If we go to the frame debugger, for this view, it takes 26 draw calls to draw it. So if you step through it, it draws the shadows, and then draws the meshes, and then draws the skybox and the UI on top of it. If we switch over to the lightweight render pipeline, it goes from 26 down to 18 batches or draw calls. So that's already, by switching to the new render pipeline, we're saving a bunch. You can see it's using less draw calls to achieve the same result. And then if we then turn on the new experimental scriptable render pipeline batching, which you can see at the bottom right corner, it's on, it goes down to 8 draw calls. So we started with 26, now we're at 8, which is like 1/3 draw calls. And of course it depends on what your scene composition is like, but this is a really, really great saving. And what happens, you can see, is all the meshes are drawn in one pass for shadows and also for the scene. All of them use the same shader, or material, and then you can see they all get rendered in one pass. And it's as simple as that. So great savings to be had by upgrading to the lightweight render pipeline. There is the caveat that for specific cases, for very simple scene setups where there's just like one directional light and not much else going on in the scene, the lightweight render pipeline performs worse than the built-in render pipeline now. But since it's still being worked on, whereas the built-in render pipeline is not being worked on, that's going to improve in the future. So it makes sense for you to already be looking into upgrading your project to this render pipeline. I said render pipeline a lot. Do we have time? 3 minutes?
About 3 or 4 minutes.
Okay. One last thing I want to show, just as an example, is the new custom pass injection you can do in the scriptable render pipeline, which makes it a lot easier to implement post-processing effects. And other effects, especially the camera stacking, is not available or not supported in the lightweight render pipeline. You can't have one camera render some stuff and then have another camera render after that one. This is not supported. So people are asking, then how do I implement this effect where I draw this with a different camera? Well, you can inject custom passes. And this is very simple, and I find much more convenient and more performant. I have an example here. Now we're at the lightweight render pipeline. On my camera, I have a blur pass script. If I just enable that, you can see the scene got blurred. And we have a simple shader that does this. But the way to do this before would have been much more complex than it is now. So let's take a quick look. Here's the blur pass. And the key thing is that it uses an interface, I after transparent pass. So this causes this class to get called right after the transparent objects in the scene have rendered. And there's equivalent I after opaque pass, for example, and I after skybox, etc. But we want to blur everything after all the transparent objects, first the opaque objects, and then the transparent objects have rendered into the scene. This get past enqueue method would get automatically called, and then you can then return an scriptable render pass where you do something. It looks like a lot of code, but it really isn't. It's mostly boilerplate. And then what I do here is get a new command buffer and get a new render texture, temporary render texture to copy the screen contents into. And then using a blur shader, which I can open right here, which is basically just averaging the neighboring pixels and then returning the result. We can just put that back into the screen buffer, and then we have a blurred result. And it's very simple. And there's a cleanup, which just returns the temporary render texture, and that's about it. So again, just about 100 lines of code to be able to implement an effect where you're blurring the entire screen. But you could also animate the parameters, and then you could have it fade in and out. So this is just a quick look into Lightweight Render Pipeline, what it might take for you to upgrade your project to it, especially if you're using custom shaders, and how you might be able to also port over your processing effects, post-processing effects that you might be using for your mobile game. That's it for my talk. Thank you for attending. If you have any questions, I will take them.